Hello and welcome to the third episode of our seminar series Back to Basics. My name is Tobias Langrock. I'm an application chemist for Waters. I've been with Waters for 16 years now. I'm based in Eschborn in Germany. And the title of today's episode is Theory of Liquid Chromatography. So I will give you really a brief introduction into chromatography, the very basics of it, and then start to look a little bit into how and what makes a good chromatography method, a good separation method. So this is what we're going to do now in the next 45 to 50 minutes. And I hope you enjoy. And let's get started. Well, I cannot start talking about chromatography without mentioning the history a little bit. So the inventor of chromatography was the Russian botanist Mikhail Tsvet. He published his work in 1903 that really described a new method that can be used for the separation and analysis of compounds. And what he did was he was able to separate chlorophylls and carotenoids from a plant extract. And he was able to see these colorful bands, and he was really amazed by it. And that's why he described his technique as chromatography. He took the term chroma from the Greek word for color, and he took graphy, the Greek word for writing, describing, and that's what the name means, really, writing, describing colors, chromatography. The way he did that is he more or less built his own first column, an open glass column, and he filled it with particles. In the beginning it was sugar like carbohydrates or calcium carbonates, but he did it with various particles. And then he poured a plant extract on top of this column. And while the liquid of this plant extract was flowing through the column, he was able to see these beautiful, colorful bands developing. And that's when he realized that he was really able to separate different compounds in this mixture of the plant extract. And that's really what it's all about. We want to separate compounds. Of course, it's not, or it doesn't have to be colors anymore, but just simply different compounds and different mixtures, but it's all about separating different compounds. And we do that in order to identify them, to really be able to say what is in my mixture, so the qualitative qualification part, and then you have the quantitation part, so how much of it is in there. That's more or less all what it's about. Separating in order to say what is in my mixture and how much of it is in there. Well, and even though chromatography evolved quite a bit throughout the years, the basic principle is still the same. We have a stationary phase, the column of Tsvet's experiment, and we have a mobile phase, some sort of solvent. And of course, this can be different types of stationary phases now, different types of particles that use different characteristics, different interactions, but it's always the same. You have a stationary phase, a column packed with materials, with particles, and then you inject a sample, a mixture, and you flush it through the column with a mobile phase. And all these compounds in your mixture have different behavior, different characteristics, and they will have various interactions with the stationary phase, with the mobile phase, depending on their characteristics, on their structures. And these interactions will be different from compound to compound. And by using these interactions, we will see a separation of the compounds. It once more, maybe a little bit more sophisticated, in order to explain how chromatography works. It's about changing or influencing the relative speed of each analyte band, of each compound, during its travel through the column. And there's always a competition between the mobile phase and the stationary phase. So by exploiting different characteristics of my compounds, of the structures, of the molecules, they tend to stay longer or better in the mobile phase, or they would like to maybe attach more to the stationary phase. And each compound does that differently. And that's how we can use that in order to separate them. So in this case here, you see that the goal is to separate a mixture of three compounds. So the yellow one here is a very polar molecule. The red one let's say, moderately polar, and the blue one is really not polar at all. It's a very hydrophobic compound. And we want to separate them on this column. So we inject the mixture, which is just a black mixture of all these colors, of all these compounds, and then we start flushing them through the column with the mobile phase. And we do that we start that experiment at time point 0, and then we measure the time, how long it takes for these analytes to separate and to come out of the column here. As soon as one of these bands comes out, elutes, we record the time point, and that's then the retention time. And that's how chromatography works. In the case of Zved's experiment, that's what we call normal phase today, probably because it was the first chromatography that was there. So normal phase chromatography means that the stationary phase itself is a polar phase. So the column is filled with polar particles. Zved did it with sugars, calcium carbonate, or I think he even started with silica as well. So silica, silicium oxide, sand-like particles. This is more or less what we still use today. The mobile phase then is a very non-polar solvent, like hexane. That means that when we introduce our black sample onto this column, the blue non-polar component likes the non-polar mobile phase much more than the polar silica phase. In the end, it even gets repelled by the polar stationary phase and simply likes to stay in the mobile phase. And that means that flushing mobile phase through the column, this blue component will not really absorb at the stationary phase, but will be flushed out first, as it simply stays in the non-polar mobile phase. The red, moderately polar compound does interact a little bit with the stationary phase, and that's why it slows down in relation to the blue component, stays longer on the column, and then elutes a little bit later. And the yellow, very polar component likes our polar stationary phase a lot, binds to it much more than the other two components, and needs much more time to get flushed out of this column, and will be the one that elutes and comes out last. And that's, till today, normal phase chromatography. Polar substances are retained on a polar stationary phase. Unpolar substances elute quickly with the non-polar mobile phase. Now, the most common chromatography today is then the, let's say, opposite of Zved's chromatography, and that's why it's called reversed phase chromatography. So in comparison to the normal phase chromatography, the stationary phase is non-polar, hydrophobic, usually by using some longer carbon chains like the C18, which is simply very, very unpolar. The mobile phase then is polar, aqueous, water, or mixtures. That means now that the yellow component, which is very polar, simply likes to stay in the mobile phase, as it is also polar, gets dissolved there better, so it kind of washes out, comes out first with the mobile phase. Again, the red one, moderately polar, not so polar as the yellow one, tends to interact a little bit with the stationary phase and stays longer than the very polar substance. And then the blue, very unpolar component simply sticks to the non-polar stationary phase with hydrophobic interactions with the C18 chains, with these particles, and then it comes out last as it's really binding more to the stationary phase. And that's reversed phase. Non-polar substances are retained more on the non-polar stationary phase, and the polar substances are washed out earlier with the polar mobile phase. So staying in this example of reversed phase chromatography, we can now start influencing, fine-tuning our chromatography by changing the polarity of the mobile phase. This is done in different experiments where we use different mixtures of methanol with water. Methanol is a organic solvent, so not so polar, more unpolar than water. And here we see different experiments using different mixtures. This is what we call isocratic mode. We use one solvent throughout the chromatography, and we don't change the composition. But we can do several experiments with different amounts of methanol, and that resembles different polarities. So here with 80% methanol, it means that the mobile phase overall is quite unpolar, not so polar. That then means that all the compounds, even the non-polar hydrophobic compounds, like this not polar mobile phase more, and they just flush out with the mobile phase and they don't bind to the stationary phase. With the other experiments, we can now see that increasing the amount of water, like here 40% water, or here 50% water, we see increasing retention of the unpolar substances, meaning they don't like this mobile phase that much anymore. They start binding to the stationary phase. And the more polar our mobile phase gets, the more they stick to the column, the more retention we get for these compounds. That's how we can influence chromatography with isocratic mode, different mixtures, different polarities of the solvent. If the separations become more and more complex, we can then start using the gradient mode, where we change the composition and the polarity of the mobile phase gradually during the separation. In this example for reversed phase, we start with a highly aqueous, highly polar mobile phase, and we retain the unpolar compounds, and we start eluting them by increasing the content of the organic solvent. So we are decreasing the polarity of the mobile phase, and therefore these compounds start going into the mobile phase and eluting of the column. And that's the gradient mode, and that's of course one of the most used modes for chromatography in order to really do complex and difficult separations. Here is a very basic schematic of a chromatographic system as we're using it today. So now we're talking high performance liquid chromatography, HPLC. That's what we're using today. So no gravity anymore, but a real pump that pumps the eluent or the mobile phase. And this pump pumps it directly into the HPLC column. Then there's a injection valve or an autosampler here that brings and injects your sample into that flow. So the pump then will pump your sample and mobile phase through the column. You will get the separation, as we discussed before, in the column. And after that, when the analyte bands, your compounds elute, hopefully separated, you will then detect them with some sort of a detector system. And of course, thankfully, this is recorded with a computer and software, the retention times. And with that, you can access the information about what is in your mixture and how much is in there. And the rest, or after the detector, your flow just goes to the waste and has to be discarded. So as a chromatographer, you will end up with a chromatogram. That's a graph over time with peaks on it, like this one here. And each of these peaks resembles a band of analytes, like this one here, that came out of your column and went through the system, through the detection cell, and was detected and translated by your software into these peaks. And notice that the narrower, the sharper, and the more concentrated these bands are, and the sharper they are contained during their travel through the system, the sharper and the higher these peaks get. And that means that you can detect them more sensitively and that you can separate them better. So if you compare that to the blue band here, that is already diffusing a little bit in your system, that would mean then that this peak will get broader, like this one here, and the peak height will decrease. But now let's move on to the question, what makes a great separation? Well, this will of course depend on the goals that you set for your method for your separation, but I guess the goal of any separation will be to have all your peaks that you're interested in well resolved in hopefully a short time and with good peak shape so you really have that good separation. And here's an example of a method for the detection of an active pharma ingredient here, the metoclopramid, and for the detection of 8 of its impurities. And you can see here it's a very short method. It's a 5-minute method, a UPLC method that detects all compounds of interest with nice separation, with nice resolution, nice peak shape. And this allows us to identify and quantify each of these components. I used the term resolution now already, so resolution is the most important term in chromatography. It defines and describes the separation of your peaks in a sample mixture. If you want to quantify, your peaks need to be separated, need to be well resolved in order to be able to determine the peak area correctly. And if you're doing preparative chromatography, meaning you are purifying substances, you need to remove your impurities. So all of this is done much easier when your compounds are well separated from each other. Here we are now getting some examples for resolution, and this is given as a value, so the resolution is really expressed as a number. And here you see resolution 0, that means no resolution at all, no separation. So you have, for example, 2 compounds eluting from your column at exactly the same time, so they are completely co-eluting. And if you start seeing some sort of separation here, this resolution value will increase. So this is roughly a resolution of 0.8, and a real separation probably starts with values of resolution greater than 1. And in most chromatography methods, a value of 1.5 at minimum is required. This then means usually that you get your peaks resolved down to the baseline, and you can really identify and quantify them separately with this so-called baseline separation here. If this value is then even greater, of course, these peaks come more and more apart and you get better separation with higher resolution. As this episode is called Theory of Chromatography, of course, there has to be an equation. And this here is probably the most important equation in chromatography. It's the equation of the resolution. Well, you don't have to calculate with this equation, but it's really good to know how you as a scientist can influence these terms and what they mean, so you can enhance your chromatography. So on the left side, it's the efficiency, N, the selectivity, alpha, and the retentivity, K. So let's just focus on the left part, the efficiency. This is more or less everything that contributes mechanically to the resolution. So everything that comes from the system, the volumes of the system, the dispersion in the system, the choice of column, particles, column length, and these kind of things, and how well the columns are packed. These all are mechanical influences on the resolution. And you see here how it will influence your separation. If the efficiency is increased, the peaks will get narrower, will get sharper, and therefore you will achieve a better separation. Usually, efficiency, column efficiency, is measured in plate counts or plate number N, and this is always related to the retention and to the peak width. Typical plate count values that you can expect for HPLC columns are around 12 to 15,000 plates. For enhanced separations with UPLC, with ultra-performance liquid chromatography columns, this can go up to higher than 30,000 plates. Important to remember is always that these plate counts are measured under specific conditions, so in a specific system with specific method conditions, and you can really just compare absolute values if you know under which conditions they were measured, so you can really compare them. As mentioned, these plate numbers, theoretical plates, are related to retention time, or here given as retention volume, not to calculate with a flow rate, but rather the overall volume, but more importantly with the peak width here. So it's divided by peak width, meaning the smaller the peak width gets, the higher the efficiency gets. And here you see that depending on where you measure the peak width, you need to apply different factors here in this equation. This yields then to the effect that in an ideal world where you have a perfectly shaped, symmetrical Gaussian peak, it doesn't matter where you measure the peak width, you will always get the same result. In the real world, though, you never get these beautiful symmetrical peaks, but sometimes they tail a little bit, so they elute a little bit slower in the end, so you will get different peak widths at different heights. So it really it's important to know where it was measured, how, and so you can really compare the values that you have. We can describe the efficiency of a column even a little bit different. So we can describe it with the height equivalent of a theoretical plate. Well, these are all concepts and models coming from distillation theory to describe resolution or resolving power. There are no real plates on a column, of course, but this concept can be taken to describe the efficiency of a column. So the height equivalent then means if a plate is larger and thicker, you can only place a few, maybe, of these plates on a specific column length, while with thinner and smaller height equivalents, you can place more plates on the same column length. And this then translates to this equation here, that the plate number, can be described by the length of the column divided by the height equivalent of a theoretical plate. And if this height equivalent now gets smaller and smaller, the number of plates increases and the efficiency of the column increases as well. The famous Van Deemter curves now compare the height equivalent of a theoretical plate to the linear velocity through the column. So this can be translated into flow rates for different column inner diameters. And you have the height equivalent here on the y-axis and the linear velocity on the x-axis. And these curves are drawn and calculated for different particles in the column. And here you see how efficient these particles can be in a column by looking at the height equivalent. And you can see where the optimal linear velocity for these particles actually is. So these are the Van Deemter curves. And the next slide will show how they are calculated. Again, one more equation, and again, you don't need to really calculate with it. It's about these three distinct terms of the Van Deemter equations that then describe the efficiency with the height equivalent of a theoretical plate. So the first one is the A term called eddy diffusion or interparticle channels. It's dependent on the particle size and completely velocity or flow rate independent. The second one, the B term, is the molecular diffusion or axial diffusion. It is inversely proportional to the velocity and the flow rate, therefore. And the last term is the C term, which is describing the mass transfer kinetics. It is directly proportional to the velocity and flow rate and to the particle size squared. Let's have a more detailed look on these different terms of the Van Deemter equation. The first one is the A term, the so-called eddy diffusion, and this describes different paths your molecules might take when they travel through the column. This is, of course, also dependent on the packing of a column. The better the columns are packed, the more consistent, the more efficient they are, but it's also dependent on the particle size. So one molecule might find a very direct way through the particles, while another molecule might take all the different deviations and channels it can find when it's traveling through the column. And in the end, they will reach the end of the column on different time points. And this describes the band broadening of your peaks. And the less you have these differences in channels, the more efficient your column will be. And as this is dependent on particle size, smaller particles will yield to higher efficiency because the paths or the differences in paths is not so big as for larger particles. The B term of the Van Dimter equation describes the axial diffusion of your bands, and it is the inversely proportional to the linear velocity or the flow rate. It simply means that if you have a lower linear velocity, lower flow rate, you will have more axial diffusion of your bands while they are traveling through the column. They have more time, and with that they diffuse more, and your peak and your band will get larger, wider, and your efficiency will decrease. It means lower flow rate, higher B term, higher height of your plate, and that will cause lower efficiency. On the other hand, if you increase the linear velocity, your molecules have less time to diffuse, your band is contained, narrower, and this will yield to sharper peaks and more efficient columns. The third term of the Van Dimter equation is probably the most complicated one. It can be divided into three separate parts. It is directly proportional to the velocity and flow rate, and it is proportional to the particle size squared. And the first part is the mass transfer of the mobile phase, or the moving mobile phase. So there's an effect that liquid that flows between particles will flow faster in the middle of these particles. It will flow slower around these particles, and with that you will get a slight difference in mobile phase flow, and therefore you will get band broadening and a decrease of efficiency. The second part is the mass transfer of the unmoving mobile phase. So in the particles there are pores, and your molecules travel into and out of the pores into this non-moving mobile phase that is in the pores. And with that, molecules that travel just a short distance into the pores and directly out of them again will move through the column faster than the molecules that have a longer travel into the pores and out of them again into the moving mobile phase. And this is particle size dependent, so smaller particles simply have shorter ways in and out of the pores, and therefore this effect of the band broadening is less and the efficiency increases. The last part now is the mass transfer of the stationary phase. There are simply differences in the adsorption-desorption kinetics of your molecules inside the pores to the stationary phase, and with that there will always be a time difference and a band broadening of these molecules when they come out of the pores again into the moving mobile phase. So these three terms then will, with increasing flow rate, will decrease the efficiency again. So the height equivalent will increase with that. It also means that smaller particles will increase the efficiency. And when you add these three terms to each other, so the constant A term, the flow rate dependent B term, and the flow and particle size dependent C term, when you add these together, you will receive the described Van Dimter curves. The easiest way for a chromatographer to influence the efficiency is the column choice. So we start with column length. If you have two columns that are packed with the same materials with the same particle size, and if you're using the same mobile phases, you will increase the efficiency when you take longer columns. So if you take a look at this 5 centimeter columns, you have more or less separation, but with the increase in column length, you will increase retentivity, and you will increase efficiency by separating these peaks better. On the other hand, if you take two columns that contain the same packing material chemistry, that have the same length and the same mobile phases, but one column is using 5 micrometer particles and the other one is using only 1.7 micrometer particles, so just a third the size of the particles, you will see an increase in efficiency. At the same time, actually, these peaks here, not well resolved, will get sharper, will get thinner, and therefore you will have a better separation. And this means you have a much higher efficiency when using these smaller particle columns. So looking now at different Van Deventer curves for different particles, again, you see why we are going for UPLC columns and UPLC systems, basically because Van Deventer tells us so. Again, decreasing the particles from 10 to sub 2 micrometer particles, you see that the overall efficiency will increase because the height equivalent of a theoretical plate decreases. You can also see that the optimal linear velocity increases with smaller particles. You have to take that into account. If you work with these smaller particles, you will need to increase the linear velocity, and this translates into different flow rates for different column inner diameters. And if you take a look at these here, the 4.6 millimeter ID columns, you would need flow rates in the range of 2 to 4 milliliters per minute for the small particles, and that's of course not very efficient for your lab, actually. So that's why, or that's one reason why we go for smaller columns, smaller inner diameter columns for the smaller particles. You have to take that into account, and that's quite important when you work with these columns. This was the first part of the resolution equation, the mechanical contributions coming from the column, the particles, using the optimal linear velocity. And now let's take a look at the other side of the resolution equation. So here we talk about selectivity and retentivity. And this is what you can influence by your method development, by your choice of mobile phase pH, by choice of the chemistry of the column, the stationary phase, and by choice of the elution solvent itself. You see an example how this will affect your separation. So you have two compounds here that are not well separated, not well resolved. By increasing the retentivity, you will shift them to higher or larger retention times. Of course, this means longer analysis time as well, but you might separate them better. But by increasing the selectivity, by really changing the overall chemistry of stationary phase, of mobile phase, you will have the greatest influence of the separation, and you might be able to separate these two compounds well enough. Selectivity is really just a way to describe the relative retention of two peaks, basically how well they are resolved from each other. So you have the retention time of peak number 1 and you have the retention time of peak number 2, and you bring them into relation, and this describes the value of the selectivity. And different columns with different chemistries will display different selectivities when used with different mobile phases. So this really shifts around the retention times of your peaks and really gives you the ability to increase and to enhance your separation. When you think about selectivity, there are several parameters that you can touch and fine-tune to change and to create selectivity. There's this triangle here where the three main parameters are described. So you have the pH of your mobile phase, you have the column chemistry, and you have the choice of the organic solvent that you can influence directly. And of course, there are different things that you can then fine-tune as well. Of course, gradients, slopes, temperatures, and these kind of things. But these three are the main parts that you will have to develop for your method. We will start with the top of the triangle, the pH of the mobile phase. Well, this can be a powerful tool for your separation of different molecules. Some of them might be acidic, some of them might be basic, some of them might be completely neutral. And with that, you can influence the state of your analytes. So if you take a look at the pKa value of your molecules, this will give you the pH at which your molecules are 50% ionized and 50% unionized. And for chromatography, you want them to be in one state. So you want them either completely ionized or completely unionized. And from that, you can take the rule of plus minus 2, meaning if you want to, or if you want to use a pH of your mobile phase, you should adjust it to either plus or minus 2 pH units from the pKa of your molecule of interest. So these molecules will be either 100% ionized or unionized. Here with this retention map, you will see why pH has such a great influence on the separation of your analytes in reverse phase. You have on the y-axis the retention factor. Higher values mean higher retention. And on the x-axis, you have different pHs of your mobile phase. You see here in black, the graph shows the behavior of a neutral compound. This compound is not affected by pH. It cannot ionize in solution, so it will not change its state. It will simply behave the same with the same retention on different pH mobile phases. A basic compound, however, is completely ionized in low pH, protonated. And with that, it will not bind to the hydrophobic reversed phase as it's ionized. If you start increasing the pH, at some point, coming over the pKa value, at some point at high pH, this basic compound will deprotonize completely and will be completely unionized. And with that, it will bind much more to the reversed phase. Acidic compounds are completely the opposite. They are absolutely unionized in very low pH, so protonated, and they will lose their proton and will be ionized at high pHs. And with that here, on high pH, they will lose the retention on the reversed phase. Now, take a look at this middle section here, where you have these sudden jumps in the states of your compounds. These regions are very unrobust regions for chromatography methods. Small changes in pH of the mobile phase, saying small errors in adjusting the pH, will have a dramatic influence on the retention of your compounds and therefore the separation. So the recommendation is stay away of these regions and adjust your pH to a value where you have your compounds either fully ionized, like here, or fully unionized, as shown here. So you have stable retention behavior. Let's have a look at another example. Again, we have the three compounds, the basic one, the acidic one, and the neutral one. And now we show the chromatograms at different pHs as well. So you have here pH 2. And if you take a look at this map again, pH 2 over here, the base is protonated, ionized, and doesn't bind to the stationary phase. The acid is unionized, also protonated, but shows retention on the reversed phase, and the neutral compound is the one with the most retention. So that's why we have this order here. The basic compound doesn't bind at all to the column, elutes quickly. The acid has good retention, and the neutral here as well. Jumping to pH 5 now, you see pH 5 over here. The neutral stays at the same retention time, absolutely unaffected by the change of pH. However, the base are now deprotonating at the higher pH, will show some retention, and by this map, we can predict that they probably will completely co-elute the acid and the base. And this is what you can see in the chromatogram here as well. One peak for both compounds, so complete co-elution. So let's go to a higher pH, and then you might probably guess how this will look like. Because now at pH 10, over here, you see that the acid is fully deprotonated, so negatively charged, doesn't bind anymore to the stationary phase and elutes first. The basic compound, protonated, unionized, binds well to the stationary phase, shows some good retention, and again, the neutral stays at the same position. This is what you can really see here. The neutral compound will always be at the same retention time, absolutely unaffected by these changes of pHs, while the acid and the base kind of shift around with these pH changes. Even further, as the compounds or different bases, different acids simply do not behave the same, they have different pKa values, you can use pH as in order to modulate the selectivity. So here at pH 2, we have two bases that show no retention. They co-elute completely in the beginning of the chromatogram. We have again the neutral compound here in the middle, and the acid, in this case, eluting last. In order to separate these bases, when we take a look at their retention behavior here in these graphs, we clearly see that changing the pH of the mobile phase to a higher pH will probably result in the separation of these two bases. And this is what we're going to see in the chromatogram. Now the acid will come first, the neutral stays where it is, but base 1 and base 2 will be separated. And that's why it's so important to use pH as a tool. There are columns out there that can or that absolutely will be robust and stable in high pHs. So it's always worth at least thinking of high pH mobile phases as well in order to gain selectivity and separation of certain compounds. Now let's take a short look at the other parameters. You have column chemistry as well. We will probably cover this part in more detail in one of the next episodes. This is just to remind you that, of course, the selection of the column will influence the selectivity. You have a lot of choices, a lot of different attributes of a column will affect your selectivity and your separation dramatically. I guess with any vendor, you have different choices of base particles. They differ in charge of the surface and in the chemistry of the particle, and this will have an influence on the retention and the selectivity, but also on the peak shape and, of course, the particle size, as we have seen, has an influence on the efficiency of the separation. So this is the choice of the particle, and probably the most known is the choice of the bonded phase. So this is really the chemistry of the column, and this will highly affect the retention of your compounds and the selectivity, but also the peak shape. And last but not least, actually the column hardware also has a great influence and a great effect on certain separations of certain compounds. For example, a steel-based column hardware might cause secondary interactions, unwanted interactions of certain analytes, especially, for example, acidic ones, that will interact with the column hardware, and this will cause, for example, peak deformation, peak tailing, and this yields, of course, to less separation. So all of these attributes have a great influence, and you can use them in your method development. Here you have a small selection of different column chemistries that you can choose from. By far the most popular chemistry is the C18 phase. A full coverage C18 column is the general purpose column. When you go to mid coverage C18, as we do with our T3 column, you have a more balanced retention, so it promotes a little bit more the interaction with polar compounds. But then there are other phases as well, like the C8, where you reduce the hydrophobicity of the stationary phase in order to get good retention of strongly hydrophobic compounds that would simply bind too much to the C18 phase. But then there's other phases as well, like phenylhexyl phases, that introduce pi-pi interactions here. The same with the fluorophenyl columns. There are also different types of chromatography, not only reverse phase, but for example here helic phases, hydrophilic interaction chromatography. These are used for the retention and for the separation of polar compounds that would not bind to reversed phase columns. So a huge selection that you have, and this will be influenced by the compounds that you try to separate, and this is one of the biggest tools that you will need in order to develop your methods and to influence your separation and your selectivity. And lastly, the choice of organic solvent also has an influence on the selectivity. Here is a table of solvents that are commonly used in chromatography. The isopropanol is pretty much dividing this table into two sections. Below isopropanol, you have solvents that are mainly used in normal phase chromatography. Above the IPA, you have the solvents that are mainly used in reverse phase chromatography. And by far, the two most used solvents in reverse phase chromatography are methanol and acetonitrile. They are used because of their low viscosity, their low UV cutoff for the detection, and with that, these two really are used in pretty much all of the reverse phase method. Let's have a closer look on these two solvents. Methanol is a protic solvent. It has the hydroxyl group. With that, it is a hydrogen bond donor and acceptor, so it is quite a polar solvent actually. With that, it's a weaker elution solvent in a, for example, reverse phase gradient, and it's also a little bit more viscous, so you have a little bit of a restriction in the flow rates. The acetonitrile is then an aprotic solvent. It has only the nitrile group, can only function as a hydrogen bond acceptor, so less polar interactions. However, it can introduce itself pi-pi interactions, which can affect the specific methods. With that, it's less polar. It has a stronger elution power in reversed phase chromatography. It's less viscous and can be used with higher flow rates then. So this slide now demonstrates the effect that you can expect when using methanol or acetonitrile. Well, as expected, acetonitrile is the stronger, has the stronger elution power, so everything elutes earlier in the gradient than with methanol. But you really do not see any change in selectivity. So it's really just the difference of polarity that will affect the chromatogram here. Everything will elute earlier with acetonitrile in comparison to methanol. This is not always the case like this, but this is the main effect that you can expect from these two solvents. This will look differently on different column chemistries. So when using a pentafluorophenyl column, as described earlier, these columns will be able to introduce pi-pi interactions themselves with your analytes, and then it makes a bigger difference if you use acetonitrile or methanol. Acetonitrile, as mentioned, can build pi-pi interaction itself, so it can more or less block the interaction of or the pi-pi interactions of your compounds with such a stationary phase. And this will mean that when using methanol with these phenyl columns, you might see increase in retention of certain compounds because of this pi-pi interaction. So especially with these columns, phenyl columns, you will or you might see an influence of the selectivity. You will see a change in elution order when changing your mobile phase from acetonitrile to methanol as the elution solvent. Well, this was all I wanted to show you, the three main parameters that you can use to modulate the selectivity when developing chromatography methods: mobile phase pH, column chemistry, and organic solvent. As I said, there will be another episode diving a little bit more in the details of method development. Of course, other parameters can be fine-tuned as well, like temperature, gradient slope, and many others. But this was a first glimpse into the method development of chromatography. And of course, we focused a lot on the most important part, the resolution, because that's what it's all about. We want to pull things apart. We want to separate. And so this is the most important part when talking about theory and about improving and developing chromatography methods.